Exercise 6-7 is trying to get you to read and understand things that are called reaction coordinate diagrams. Reaction coordinate diagrams track how energy changes over the course of a reaction. So you'll always have a y-axis that will be some type of energy. So the energy increases as you go up. Sometimes on standardized tests you may see a delta G there, sometimes a delta H. It doesn't really matter. The y-axis is always some type of energy. The x-axis is the progress of the reaction. An abbreviation for that is Rxn. So Rxn is just an abbreviation for the word reaction. So it's not necessarily time, it's just the progress of the reaction. Okay, there are a few things you want to be able to tell here. The first is you want to be able to tell whether a reaction is exothermic or endothermic. The reactants will have a certain amount of energy, and the products could either have more energy or less energy. If the products have more energy, where did they get that energy from, that extra energy? They got it from the surroundings. And so that's an endothermic reaction. If the products are higher in energy than the reactants, then the reaction is endothermic. If the products are lower in energy than the reactants, then that gave away a certain amount of energy. Where did the energy go? It went to the surroundings. That's an exothermic reaction. So if the products have less energy than the reactants, it's an exothermic reaction. So that's the first thing you'd want to be able to read on these diagrams, comparing the energy of the reactants and products and telling whether the reaction is endothermic or exothermic. Now, if you have a molecule to start with, that molecule is kind of stable. If it weren't stable in any way, it would immediately react with something and change. So it is kind of stable. If you were to look at a gigantic energy diagram for the universe, you'd have the bottom where everything is spread out evenly, it'd be homogeneous. You'd have the top where everything is all in one place. And you can imagine it being ultimately a downhill slope, but on the way you'll have little pockets. And each of these pockets is a slightly energetic way that something, or a slightly stable way that something can exist for a brief period of time. So anything that persists for any time in the world has some stability and exists in one of those little pockets. And you would have to add energy in order to destabilize it enough for it to turn into the products. So it's stable, 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 pump in energy, starts twisting, turning, vibrating, knocking into stuff enough. Finally, it gets to that high point, and once it has that much energy, it quickly turns into the product. The energy that you need to pump into the molecule in order to make it react, that's called the activation energy. The symbol for that is E sub A. The activation energy is how much energy you need to pump into that reactant in order to destabilize it enough for it to react. Notice that it's only the activation energies that let anything persist in the world at all. Everything in the world would be pureed, it would be evenly homogeneous if there were no activation energy that allowed molecules to get stuck for brief periods of time in these little low energy holes. So that's the activation energy. Now you can think of the forward reaction and the reverse reaction. And the activation energy that we have here, this is the activation energy for the forward reaction. Imagine thinking of the activation energy for the reverse reaction. You start with this much energy, you have to get it all the way up here. It's a much higher activation energy. Now, the activation energy gives you some information about the speed of a reaction. The smaller the energy, the smaller the activation energy, the more often you'll find a molecule in the universe that has that energy, and the more often that reaction will happen. So in this example, the forward reaction, which has an activation energy that's only that big, will happen faster than the reverse reaction, which has a much larger activation energy. Imagine balls being moved around just at random rates. more often the balls will go in the right direction than in the left direction. If you're just waiting around randomly, the balls will go over here faster than they'll go in the opposite direction. Because the hill that they would have to go up, the energy barrier that is in front of them, is bigger in the reverse reaction. So the size of the activation energy tells you about the speed of the reaction. So far we have two pieces of information. We can tell by comparing the reactants, the energy of the reactants in the products, whether a reaction is endothermic or exothermic. And second, we can see how big the activation energy is and get a sense for how fast that reaction is going to happen. There are two other features of these reaction coordinate diagrams that you want to recognize. The first one is this highest energy state, the point where the reactants transition from being reactants to becoming products. That is called the transition state. It's the most energetic form of the molecule during the whole time that it reacts. The symbol is one line with two horizontal lines, and usually when they draw those molecules, they put them in brackets with that little cross at the top right of them. And that's telling you this isn't really a molecule, this is just the transition state as the molecule is turning into the products. What does the molecule look like at the transition state? Well, it more closely resembles whichever thing it's closest to in energy. So for example, this transition state is closer to the reactants in energy than the products. So it's going to resemble, it'll look a little bit more like the reactants than it will the products. Okay, one other feature of these reaction coordinate diagrams. You might have reactants with a certain amount of energy, products with a certain amount of energy. You have to enter enough activation energy to get it going, but then there's a little intermediate, kind of like what we were talking about for the whole universe. This little valley area is called an intermediate. Let me actually use a different color for that. That valley area is an intermediate. So the process at the top, that reaction all happened in one step. But you could see that this reaction is happening in two steps. The first step has its own activation energy, its own transition state. The product for the first step does not exist for very long. It's still very high in energy. There's a smaller activation energy for this reaction, a second transition state, and then you get the final product of the reaction. So this is happening in two steps. And how the molecule looks in between the two steps, that's the intermediate. Now, just to clarify the difference between a transition state and an intermediate, if you imagine just jumping up and down from the floor, there's a point in your jump where you're higher. You get the highest you get, and you're going up when you first jump, and then you're eventually going to fall down. At that highest point, you're right in between going up and going down. And that's like what the transition state is. You never exist at that highest point. You never stay at the highest point. It's just a moment of change. You're going up, at the highest point you change, you're starting to go down. That position doesn't persist for a very long time. On the other hand, imagine jumping up onto a chair, standing there for just a couple seconds, you're not going to spend the day on the chair, and then jumping back down. Existing on that chair is like an intermediate. It does exist for a little bit of time, but not for very long. So that's just maybe a little clarification on the difference between the transition state and the intermediate. So let's use that information that we learned about how to read these reaction coordinate diagrams to answer these questions. So it says, consider the relative energy diagrams, the reaction coordinate diagrams that they give you for 4 different reactions, A, B, C, and D. In this first question, it says, compare A and D. Assuming all of their factors are identical, identify which process will occur more rapidly. So we're looking at the activation energy. In A, the activation energy is that large. In D, the activation energy is smaller, and so the reaction in D will occur more rapidly because it has a smaller activation energy. In other words, molecules don't need as much energy to change from being the reactants to the products. So you'll find molecules with enough energy more often, and the reaction will happen faster. Okay, B. It says compare energy diagrams A and B. It says which process will greatly favor products at equilibrium? Well, let's look at what's more stable. In A, the reactants have a lot of energy and the products don't. Because of that, the products, lower in energy, are more stable. In B, the reactants and the products have the same amount of energy. So there's no reason so they're equally stable, and there's no reason for the reaction to favor either one. This would be like having a delta G of 0 or having a K of 1. So the reaction that favors the products is reaction A. So you could say the reaction in A will greatly favor products at equilibrium because the products are lower in energy in other words, more stable than the reactants. And so that would be how you would read the reaction coordinate diagrams to answer that question. For C, it says, do any of these processes exhibit an intermediate? Well, we don't see any dip there. We don't see any little dip in between the two humps. There's only one hump in each of these. In other words, there's only one activation energy, only one transition state, there's only one step in the reaction. So none of the processes exhibit an intermediate. Do any of the processes exhibit a transition state? Yes. Every single one of these processes exhibits a transition state. It's the highest point of the hump where the reactant has enough energy to turn into products. Every single one of them. So all of the processes exhibit a transition state, and the explanation for this could really just be a description of how you view those, how you notice each of those on a reaction coordinate diagram. So an intermediate is a dip in between two peaks. And a transition state is the highest point of a peak. So none of them have a dip in between two peaks, and they all have a highest point on their peaks. So none of them have an intermediate, but all of them have a transition state. For D, they say compare energy diagrams A and C, in which case will the transition state resemble reactants more than products. So here we're looking for A and C. So we have A, we have C. They want to know in which case the transition state will resemble reactants more than products. The transition state resembles whatever it's closer to. So in A, it'll resemble the reactants because it's closer in energy to the reactants. And in C, it'll resemble the products because it's closer in energy to the products. So, which one will resemble the reactants more than products? The transition state in A will resemble reactants more than products because it is closer in energy to the reactants than to the products. Okay, so just because my pencil is dying, I want to make sure I get through all of these, so I'm going to give the explanation for these in words rather than writing them all out. For E, for these next ones in words, for E it says compare energy diagrams A and B. Assuming everything else is identical, explain which one will happen faster, A or B. So if we look at A and B, we're looking for the transition states. Notice the activation energies, forgive me. The activation energy in A is much smaller than the activation energy in B, and so A will happen faster than B. Now you would want to write down the whole explanation, but here I'll just put the answer, identify which process will occur more rapidly, A, and the explanation is that the activation energy for A is smaller, so you'll find molecules more often that have the energy to go over that and turn into products. In other words, the activation energy is smaller for A, so reaction A happens faster. For F, it says compare B and D. Which process will greatly favor products, and explain. So we're doing B and D. So B and D. Which one greatly favors products? Well, in B, the reactants and the products have the same energy, so neither are favored. But in D, the products have much lower energy, therefore they're more stable, therefore they'll exist more often, and they'll be more favored. They'll be more present. So D, reaction D greatly favors the products, and the explanation that you would want to write down is that it greatly favors the products because the products are lower in energy and therefore more stable than the reactants. Whereas in B, the reactants and products have the same amount of energy and therefore are equally stable and will exist in about equal concentrations. And last, for G, it says compare energy diagrams C and D, in which case will the transition state resemble products more than reactants. So we're looking at C and D, and we want to know which one will favor, in which case will the transition state resemble products more than reactants. Well, in C, the transition state will resemble whatever it's closer to in energy, and that's products. In D, the transition state will resemble whatever is closest to it in energy, and that's reactants. So in this case, the transition state that more closely resembles products is C, and you would want to write down the explanation, which is that the transition state in C is closer in energy to the products, and so it will look more like the products. So this is just some practice reading these reaction coordinate diagrams. We'll use them in the future to describe energy changes that happen over the course of a reaction, and so it'll be useful to have this, to be able to interpret them easily.